Stanford University.
All right, so let me just tell you a little bit about the origins of string theory. The origins of string theory really were in hadron physics. They did not have to do with quantum gravity. They had to do with protons, neutrons, mesons, particularly mesons. In fact, the theory was put forward at a time when it really wasn't even known that for sure, it was suspected, but it wasn't known for sure that protons and neutrons, mesons and so forth had a quark content to them. It was suspected that a meson was a pair of quarks. The idea of gluons did not yet exist. The idea of gluons, well, in fact, it actually did. But nobody paid too much attention to it. Nembu had postulated something like it. But gluons were not part of the standard discussion of hadrons in, let's say, around 1969, 1968, 70. What was part of standard hadron physics was an interesting fact that the number of particle states was large. There was the proton and the neutron, of course. I'm not interested in the difference between proton and neutron. Just think of them as one thing, the nucleon. And then there was another particle which was very similar to the proton and neutron, had a little more spin and a little bit heavier mass. And then there was another one above that with a little bit heavier mass and a little bit larger spin. People drew pictures, diagrams. They were called Chu-Fauci plots. And they were diagrams which indicated the spectrum of objects like a proton, for example. And they plotted horizontally here, let's see, they plotted vertically angular momentum and horizontally the square of the mass. Who decided to put the square of the mass there instead of the mass? Nobody. The diagrams had a nicer look to them if you plotted mass squared. And what was discovered experimentally, this is an experimental fact, I'm getting my P's and my F's screwed up today, an experimental fact that the spectrum of particles, okay, let's start with the proton. That has half a unit of spin and a mass of 1 in certain units, namely the unit in which the mass of the proton is 1. That's approximately 1 GeV. Incidentally, at that time, the GeV didn't exist. It was the BeV for billion. Now it's giga. Okay? And so the proton and the neutron were over here. A mass of 1, mass squared of 1, and an angular momentum of 1/2. Then there's another particle with angular momentum 3/2. These were fermions, and so their angular momentum is quantized in half integers. And so there was another one up here with a little bit bigger mass, another one, and another one. And rather remarkably, these particles all formed a straight line in the plot of L versus M. Now, I should tell you, when Chu and Fauci first put this forward, the logic of drawing a straight line, there were only 2 points on this plot. And they thought it was a theorem that through any 2 points you could draw a straight line. Well, it is a theorem, but these guys were not the smartest. Well, they were pretty smart, but and so they said, oh, there's 2 points. Let's draw a straight line through them. And miraculously, as experiment went on, the additional particles all landed on the same line. What? In M squared, yes, they actually said in M squared. They plotted it as a function of M squared and L and said 2 points, let's draw a straight line. And that worked out just fine.
But I mean, that explains why M squared is the axis there, because they're hypothesizing L is proportional to M squared somehow.
They were. Why did they postulate that instead of L proportional to M? They were lucky. They were lucky, or else they had some deep. No, it wasn't. It wasn't entirely luck, and it wasn't a stupid guess either. There was some interesting reasons for it. But the same pattern held true for all hadrons, or at least for all hadrons that have been studied in detail. For example, the pi meson. The pi meson also exists on a trajectory. These are known as Regge trajectories, R-E-G-G-E, for the Italian physicist Tullio Regge. They're called Regge trajectories. And if you plotted the meson spectrum, the meson spectrum, mesons are bosons, so the angular momenta were integers. For example, the pi meson has almost zero mass. Its mass squared is even smaller than its mass. It's true, in units of GeV. All right, so the pi meson was almost massless with almost zero angular momentum. And then there's the next one up. I forget what it's called. I don't remember what the next one is called. I used to know, but I don't remember anymore. The next one up, and the next one up, and 5, 6, 7 particles along a trajectory like that. The rho meson, which was another meson, which starts with angular momentum 1. Also, same pattern. And what's more, all of these trajectories were parallel to each other. They were parallel to each other, which said whatever this m² thing is, it takes exactly the same energy, well, not exactly, but approximately the same energy to increase the m² by to increase m² when you increase the angular momentum. In other words, the spectrum was quantized. Of course it was quantized. These were particles, and this is quantum mechanics. The spectrum was quantized, but in each case, the same relationship between L and m², and the same quantum jump in m² when you increased L by 1 unit. 1 unit now means in units of Planck's constant, of course. Okay. So there's something going on that was giving rise to large numbers of particles of higher and higher angular momentum. Higher angular momentum is not that uncommon. You take a basketball, you leave it at rest. That basketball has a certain energy and therefore a certain mass, and you could plot it someplace. And now you spin the basketball. Give it 1 unit of Planck's angular momentum. That's not easy to do, incidentally. But when it has some angular momentum, it will be rotating. It will have some rotational energy. So if you increase its angular momentum by 1 unit, you will have to increase its energy by a little bit. Tiny, tiny bit for a basketball. And you can keep increasing the angular momentum of the basketball. As you do so, the energy will increase. In fact, it will not look like a straight line. It will look like a curve. And it will end somewheres. Why does the curve end? The curve ends simply because at some angular velocity, the centrifugal forces are so large that the basketball will just be torn apart. Right? So it ends someplace at some high angular momentum, which represents, the strength of materials. How strong is whatever basketballs are made out of. So trajectories like that were not unusual. You can plot them for atoms. Atoms also have the property that as you increase their angular momentum, you increase their energy, their mass, energy and mass being the same thing. But again, for an atom, there's only so much mass you can give it before you ionize the atom. Okay? So what was unusual, particularly unusual, and again, incidentally, for atoms, they would not be straight lines. What was unusual here was the simplicity of the formula, or the simplicity of the observation, rather straight lines. I mean, they were all straight and parallel to each other. And
when you say parallel, I mean, how do you mean?
I mean that if you were to plot the meson, or the baryon, or the proton, or the neutron, or the pi meson, or the rho meson, its excited states would form the same line. In other words, you take a family of particles, same slope, and it was called the universal Regge slope. Same for bosons and fermions. Same for different families of bosons and fermions. Now, this is strictly for those objects which are hadrons, those things made up out of quarks and gluons, which we now today recognize as being made up of quarks and gluons. That was one observation. The implication of this observation was fairly clear, even though it was misinterpreted at the time in many quarters. It was fairly clear. It said that hadrons were composite, that you could spin them up. This is not something you can do with an electron. There is no excited state of an electron with higher angular momentum, at least not within current experimental bounds. So electrons are like points. You can't spin a point. Spinning a point doesn't mean anything. Turning a point, you can spin a lump. So somehow these objects were not simple point particles. That was the message that should have been, and then in many quarters was taken from this. And in fact, that they had a stretchability that from this picture you could deduce, if you wanted, and we will, you could deduce the fact that they deform as they spin. You wouldn't, it's not obvious from here, but you can. All right, but there was something else. There was another observation, which was a very bizarre observation. Let me describe it to you in terms of meson-meson scattering. Let's take meson-meson, and then for particular, let's take pi-meson scattering. Here's a pion coming in, a pi-meson. Let's call it pi. Doesn't matter whether it's pi plus, pi minus, doesn't matter. And it scatters off another pi-meson. There is a particle called the rho meson, which, while it's not a composite of two pi mesons can come together at a vertex in a Feynman diagram and make a rho meson. Let's make the rho meson like that. We're going to talk, we may or may not talk more about these mesons. It's not important. The idea is important, but the particular names are not important. Rho meson. And then that pi meson could, then that rho meson could materialize as a pair of pi mesons again, this being a Feynman diagram, conventional Feynman diagram, and it would govern the properties of pion-pion scattering probabilities. Okay, that was the first thing. Now, these are all pions here. Any quantum field theorist would immediately tell you, if you have this diagram here, where the two pions come in this way and make a rho meson and then go off as two pions, there will be another diagram which looks like this. It's just the same diagram turned on its side, where a rho meson is exchanged between two pi mesons. In this case, a rho meson jumps from here to here, and this, without the pions ever annihilating. But this is just the same diagram turned on its side, and if one exists, the other has to exist. That's a consequence of principles of quantum field theory. So that's something that, that everybody believed. But then, once it was recognized that this rho meson was not a unique creature, but came along with this whole family, this whole regitrajectory of excited states, it became clear that there was no reason to only have a rho meson in here. You could add together all the various, you could add pi mesons come in, form not the rho meson, but the next excited state of the rho meson, or the next excited state of the rho meson. And so actually when you draw this diagram, you're really committed to adding up the contribution of all the mesons along here. Likewise here, if you can exchange a rho meson, you can also exchange all the excited states. Well, there was something very, very suspicious, very, very peculiar when people numerically went to do this. They actually added up from known experimental data the contributions of the rho meson, the rho prime meson, the rho double prime meson, and so forth and so on. They did that, and they did the same thing for the exchange of the row meson, and they found something rather remarkable. They found that to some approximation, the sum over all the row mesons going this way gave rise to about the same thing as the sum over all the row mesons and its partners going in the opposite, in the other channel, it was called. Okay? In other words, it appeared to be overcounting. All you needed to represent the data and all that you needed to represent the physics of pi-pi scattering was summing over rho, rho prime, rho double prime in this annihilation process, annihilation and recreation process. And in fact, you didn't need to add this in because this already seemed to contain it, numerically. On the other hand, it was also true that you could ignore this altogether and add all this up. And again, get the right answer, get something which looked pretty much like experimental data. That was very peculiar. Any quantum field theorist would look at this and say, how rubbish. If you have this, you have to add that. You have to add it. You don't get to say it's this or this. You get to say it's this and this. Okay? But peculiarly, when you added up all these contributions, it simply gave you for free the effects of another diagram here. For that reason, I and other people began to draw diagrams which looked not so much like Feynman diagrams, but which looked more like this. We didn't know what we were doing. We were just saying, look, something's going on here. First of all, we had the idea that there were quarks. Quarks were not a new idea. And we said, what must be going on is there must be a picture which looks something like this. Replacing the Feynman diagram, this would be a quark, this would be an anti-quark, this would be a quark going this way, an anti-quark going this way, and likewise over here. We drew diagrams like that. Now, it took some time for us to think about filling in what goes on in here. We just drew pictures like this, and we said, look at this. If you think about somehow what's going on has a topology, let's call it a topology, which looks like this, then look, if you cut it this way, if you imagine slicing it in an instant of time, time is running upward, of course, in all pictures, Feynman diagrams, time we're allowing to run upward. If you slice this right through the middle, then you see something that looks like a Feynman diagram in which two particles come together and join and make another particle. If we think of particles as pairs of quarks, then this figure here can represent a picture like this. On the other hand, if we take that same picture and slice it this way, it looks like a picture in which something is jumping across. Slice it the other way, it looks like these two particles produced a thing which jumped from this side to this side. So this was kind of the origin of pictures. One more ingredient was added. It was just added for fun. And just a curious question. If there are these quarks, what's holding those quarks together? Well, maybe it's something in here. These are space-time diagrams, of course. Maybe something is bridging between the quarks. And if so, then when you slice through these diagrams, then what you would see is two quarks with something bridging between them. And that something, of course, would have the structure of something one-dimensional connecting a quark and an anti-quark. A string and a pair of quarks. If you cut it the other way, that same two-dimensional sheet here could be sliced into a picture where a string was exchanged from one side to another. This was the very crude origins of the idea of string theory. In fact, it isn't exactly where it came from, but it could have. It did, to some extent. Different people thought of it different ways. So what's more, once a hadron is a string with two quarks connected to it, you can spin it. Something you can't do to an electron. You can spin it. You can try to calculate, with some assumptions about the nature of the material forming the string, its elasticity, its various properties. You can start asking how the energy of it, what kind of energy is there, incidentally? First of all, is kinetic energy, and second of all, is stretching energy. So with some kind of assumptions about the nature of these strings, or this material in here, you can start asking questions about how the energy increases as a function of the angular momentum. Surprisingly, with a relatively simple assumption that we're going to do, and we may get to it today, I hope we get to it today, we'll see that these pictures are not as arbitrary as they might seem. L versus m squared, or linear function of L versus m squared, is exactly what you need. Now, yeah.
Why did you suggest that it was something like a string, something new, rather than a normal particle exchange between the two quarks? That's how you get
Well, this is not a particle exchange. This is something that's sitting there, all the points of it between the quarks. This is, if you were to slice it at an instant, in other words, take a look at it at an instant. Here it is at an instant. It consists of a quark, an antiquark, and a whole bunch of stuff in between. Now, that bunch of stuff in between might have been a collection of particles that are forming a string, that are forming a string-like thing. They might, no prejudice about whether it was truly continuous or whether it was just something which was approximating something continuous in between. But there was one thing that made you think there might be something more fundamental about it than just a shoelace. And that was that, as far as we could tell, these trajectories didn't end. If you take a shoelace and put a pair of golf balls at the opposite ends of it and spin it around, eventually you'll come to the point where it breaks. And as far as could be told, these rigid trajectories did not break. So it seemed maybe that there was something new going on. Yeah.
Can the standard model accurately describe pion scattering?
To the extent that the standard model gives rise to a string-like behavior, it can. Yeah, the standard model can describe a great deal about pion scattering these days. Yeah, depending on the energy. At very low energies, the standard model has a very good description of pion scattering. As the energy goes up, where you start getting into the issues of these particles being exchanged back and forth, the standard model begins to get a little bit more difficult to deal with, and a string-like picture becomes more useful. No.
Did they know that the trajectory does not end?
No, of course not. No. But didn't give any sign of giving out. And, so what that meant, what it appeared, is this thing could be stretched more or less indefinitely without much happening to it. We'll come back to this point. Well, in fact, they're not entirely different than gluons. In some sense, they may be collections of gluons. In fact, they have to be collections of gluons. The present understanding of it today is something like this, that the gluon field is like the Maxwell field. All right? The quarks, you asked me about bar magnets. Okay, so the quarks are like poles of the north pole and south pole of a bar magnet. North pole, south pole. You can't have monopoles. The only way you can have a north pole or south pole is to have it as the end of a bar magnet. Okay? Or you could say it a different way. You can have dipoles. You can have magnetic fields which look like this, Here it looks like there's a magnetic monopole, lines of flux spreading out. Here it looks like there are lines of flux spreading out. And there might be some reason why the lines of flux form a narrow tube in between. The current understanding of the connection between gluons and these strings goes something like this. Quantum mechanically, fields can be described as either particles or fields. Let's take the field description. In the field description, the gluon field between two quarks, a quark and an antiquark, would be like the field configuration between a particle, between a charge and an opposite charge. It would look like this. That's what the field between a positive charge and a negative charge looks like. The energy as you separate them is the energy stored in the field in between. Now for ordinary electrodynamics, those field lines spread out, and because they spread out, the field diminishes in between them as you separate the field, as you separate the charges. Right. The field lines spread out, the field diminishes in between, and that's the usual pattern. Our understanding today is that the nonlinearities, we've talked about this before, but I'll just mention it again, that the nonlinearities in quantum chromodynamics have the effect of causing these field lines to attract in a certain way. And the effect of it is that the field lines form strings that look like that. As you pull these apart, the string doesn't spread this way, it just gets longer and longer and longer. That's our current understanding, and if you like, it's permissible to think of the string as being made up out of gluons. As you pull it apart, it's not like a shoelace or a rubber band. As you stretch a rubber band, the number of molecules in it doesn't change. The number of molecules in it, and they just stretch. And eventually, because the number of molecules doesn't change, eventually they get too far from each other and bang, the rubber band breaks. But imagine a rubber band in which as you stretched it, every time there was a gap opening up between atoms, a new atom was inserted in between. In that case, you could imagine that you could stretch this ad infinitum forever without breaking it. And that's the nature of the gluon field between a quark and an antiquark. As you stretch it, the energy of stretching goes into creating more gluons in between. And you can just stretch the hell out of that system and it won't break. Yeah.
Can you extend that analogy to say that the string that makes up, say, an electron is somehow composed of gluons as well?
It's composed, well, first of all, we don't know that electrons really are made of strings. No, all of this physics was taking place on a length scale of the size of a proton. This is an enormous length scale by comparison with the scales of quantum gravity, which take place at the Planck length. It's a more or less, perhaps accidental fact that, that the mathematics of string theory has described both things. They're quite different. They occur at completely different length scales. But through these considerations, other people began to work out the mathematics of interacting strings. Can you really quantify this? Can you really make a theory of interacting strings which will give you all of the physics of the interacting hadrons? The answer at the time is it looked promising. It looked very promising. In fact, it kept promising and promising and promising, like string theory today. Huge promise, but never quite did it right. Okay? For reasons that in hindsight are fairly clear. The precise mathematics that we were using was not quite the right mathematics for studying hadrons. It was the right mathematics for studying quantum gravity. And so we kept getting, as much as we didn't want it, we kept getting particles in the theory with 0 mass and spin 2. What is that? A graviton. Nobody wanted a graviton. This was a nuisance. Go away, graviton. We couldn't make it go away. Nothing we could do could make it go away. And eventually some smart guy named John Schwartz and Joel Shirk and said, wait a minute, maybe we're being dumb. Maybe this is a theory of quantum gravity and not a theory of hadrons. Incidentally, string theory of hadrons finally has been put together with the proper mathematics. It does work, but it's a little bit different. Okay, let's talk about, well, okay. Before talking about strings, the mathematics of strings, let's talk about relativity versus non-relativistic kinematics. Oh, incidentally, just a buzzword. This two-dimensional structure in here, which is, what is it? It's replacing the idea of a world line. A world line is being replaced by a two-dimensional sheet. Such a sheet, I think the term actually goes back to me, was called a world sheet. Today it's the standard terminology. So strings are world sheets looked at an instant in the same sense that particles are world lines looked at an instant. So that's the jargon. World sheets and world lines.
Sir, can I go back to that diagram?
Okay.
Be that there's a string in there, as it stretches, and that put the gluons in tension.
Yeah.
And so how do you get from a plus to a minus?
Well, the lines of flux come out one side and go in the other side. Same way you go from a north pole to a south pole in a magnet. No, any magnet. Any magnet has two poles. There's always two poles of opposite sign. No magnet has two north poles. No magnet has two south poles. Every magnet has one north pole and one south pole. North and south are like plus and minus.
Is there a block wall in there?
A what?
Is there a block wall in there?
A black wall?
Block, B-L-O-C-H?
I don't know what a block wall is. Despite the fact that I'm the Felix Bloch Professor of Physics, I don't know. Yeah.
Could a string be considered either continuous or discrete, or does it make any difference in this?
Well, you see, now you're running into the subtleties of quantum mechanics. Is the electromagnetic field a continuum? Well, in some ways, yes. Is the electromagnetic field made of discrete quanta? Yes, in some way, yes. Quantum mechanics tells you that that distinction between continuum and discrete is a very subtle one. And I won't try to answer it right now. I think both are true. It's continuum and it's discrete, depending on the way you think about it. All right, next question. Non-relativistic versus relativistic kinematics. Or kinematics are simple ideas about particles, energy, momentum, the symmetries of motion, on the face of it, relativistic and non-relativistic physics look very, very different. Of course, we know that they're connected to each other, but let's quantify or discuss that difference. Yes, yes. Michael, you can always ask your question. As long as you keep bringing me cookies.
String being a point in time at the world sheet.
Yeah.
Okay. If you change the angle of that cross section of space-time, do you still describe what you get as something like a string?
Yes. Yes. The Lorentz transformation of what you're talking about is the Lorentz transformation, of course. The Lorentz transformation is a moving string, but it's still a string. Absolutely. Right. So if you were to consider a frame in which simultaneity was this line here, you would still be seeing a string, but you would be seeing a string in motion, as opposed to standing still. Right. When I say standing still, incidentally, I mean the center of mass of it standing still. Strings wiggle a lot. They've got a lot of tension and they vibrate a lot, so they don't stand still. But the center of mass can stand still. All right, let's come now to the issue of relativity versus non-relativity. How do you describe a relativistic string? Well, that's awfully complicated. Describing anything relativistically is complicated. For example, let's begin with the energy of a particle. The energy of a particle, non-relativistically, point particle, is p squared over 2m. Momentum squared, depending on the number of dimensions, we would have to add up the various components of momentum divided by twice the mass. That's a nice simple algebraic quantity. The square of a function is easy to compute and so forth. You might add to this a constant. And the constant you would think of as the binding energy or just the energy of the particle because it's there. So you might put something else there. Let's call it B, the energy that it takes to assemble a particle, whatever it is. The characteristic of it is that it does not depend on the state of motion. It doesn't depend on P. In a relativistic theory, there's a natural candidate for what this B is. It's the energy of a thing when P is equal to 0, right? I mean, relativity or not relativity, it's the energy of the particle at rest. What do we, in the special theory of relativity, what do we put there? MC squared, of course. So there's a natural thing to put there, which would be MC squared, but let's just think of it as a additive constant, and it's constant only insofar as it does not depend on P. It might vary from different kind of particle to different kind of particle. It could be the binding energy holding together an atom. It could be whatever, but it doesn't depend on the overall motion. And for many purposes, you could just drop this because it's always there, and it doesn't, energy differences don't depend on it. So P squared over 2m. And P squared over 2m is terribly easy to manipulate. It's just a thing that it's just quadratic. Of course, if you have many particles in a system, then what you do is you add up the energy, if they're not interacting, and you also add up the internal binding energy, internal energy you could call it. You add them all up. Again, this doesn't matter because energy differences are insensitive to it. Now, how do we get this from relativity? Let's remind ourselves what the formula for the energy of a particle is. The energy of a particle, this is E. All right, in relativity, it's equal to the square root of p squared plus m squared. It's, of course, I'm going to correct this in a minute, but it's, of course, equal to the sum over all the particles. Let's just write it as E equals the sum over all the particles in the system of p squared plus m squared, where p squared is px squared plus py squared plus pz squared, or however many dimensions we wish to take into account. Well, why take into account? However many dimensions are appropriate to the problem. So this would be pi and mi for the ith particle, and also x, y, and z, and whatever else. Okay. How do we go from here to here? Well, first of all, I left something out. I left out c to the fourth. That's the fourth power of the speed of light, and m squared, c squared here. As soon as I finish this one little demonstration, I'm going to set c equal to 1.
Maybe 4 and 2 are switch.
Yeah.
4 and 2 are switch?
Yeah, it should be.
Do I have it wrong? You're right. Sorry. mc squared. Yeah, c to the fourth. Very good. C squared. P squared, C squared, M squared, C to the fourth. Good. Boy, I would have been in trouble. Okay. The non-relativistic limit is appropriate for problems where a particle is moving very slowly, which means its momentum is very small, and in particular in which P squared, C squared is much smaller than M squared, C to the fourth. Under those circumstances, you can take the square root of p squared plus m squared and write it first in the form m squared c to the fourth times 1 plus p squared c squared over m squared c to the fourth. You can factor out of the square root the m squared c to the fourth, and that gives you mc squared on the outside. That's a good sign. But with a correction. And the correction is this over here. What do you do with it? You expand out the square root. You use the formula that the square root of 1 plus a small quantity is 1 plus the small quantity divided by 2. Square root of 1 plus a small quantity is equal to the 1 plus the small quantity over 2. That's an approximation, of course. It's not exact, but as the small quantity gets smaller and smaller, it becomes better and better. So what do you get? You get mc squared plus p squared c squared over mc squared mc to the fourth divided by 2, all times mc squared here. Okay, so let's see what cancels. mc squared, that's familiar. That's the relativistic rest energy. But this here has 4 powers of c in the numerator, 4 powers of c in the denominator. C goes away. It has 1 power of m in the numerator, 2 powers of m in the denominator. Cancel them. Then you get the good old non-relativistic formula. But it's an approximation. It's an approximation, and when is it good? It's good when all particles are moving slowly. It's not just the whole system which has to be moving slowly to use non-relativistic physics. You might, for example, have a box of particles, and the box may be moving slowly, but inside the box, the particles may be moving with close to the speed of light. You cannot use pure non-relativistic physics for all of these particles because they have relative motions which are up near the speed of light. So strictly speaking, the non-relativistic limit is a good thing to do when all of the particles are moving slowly, and it is an approximation. Now, there's another sense in which non-relativistic physics is an exact description of relativistic physics. So I'm going to show you this. This is something that goes back a long ways in particle physics. When I worked on it in 1968 or 67 or sometime, it was called the infinite momentum frame. Now it's called the light cone frame. So if you look up a light cone frame, you will see these things described. Okay, but it's easy. It's easy. If I don't want to do it in enormous generality, it's easy. And here's what the trick is. Instead of thinking of a system in its rest frame, when we said, or near the rest frame, in other words, a frame in which every momentum is slow, we're going to do a different trick. We're going to look at it from the point of view of a frame where everything, the entire system, has been boosted up to have huge momentum along one axis. In other words, boosted up so that it's moving down the z-axis. Let's take that to be the z-axis, so that it has humongously large momentum along the z-axis. There's no loss in generality there. We can take any system and just boost it so that it's along the z-axis, and then rewrite what this formula looks like. Okay, so I'm going to set C equal to 1 now. I'm not going to bother keeping C. The energy is the sum of all the particles of, again, square root of p squared plus m squared, which is equal to square root of pz squared plus px squared plus py squared plus m squared. But now we're boosting the hell out of this system along the z-axis until every single particle has a huge momentum along the z-axis. Every single one of them. If there's any particle which is going backward on the z-axis, you just haven't boosted it enough. just boost it more until it's going forward with a large momentum. In that case, all of the PZs are very large. What happens to PX, PY, and M when you boost something? Nothing. That's the rest mass. We don't even speak about moving mass anymore, the rest mass. And the components of momentum perpendicular to the boost don't change when you boost something. Okay, so now the big quantity is PZ, and PX, PY, and M are kept fixed and are much smaller than PZ. So the appropriate thing to do here in taking the limit is expand it for large PZ, expand it for this being small. The way to do that is to write this in the form square root of 1 plus, let's just call it p square, px, well, let's write it out, px squared plus py squared plus m squared divided by pz squared, all times pz on the outside, right? Pz on the outside. If I brought the pz inside the square root, it would have to be squared. It would be pz squared, and then it would cancel this pz squared here. Okay, what's the next step? Expand. Use the binomial expansion, the binomial approximation, to do exactly the same thing we did over here. This is now the small quantity, and so this becomes pz times 1 plus px squared plus py squared plus m squared over twice pz. Twice pz squared, excuse me, pz squared. Or to summarize it all, the energy is the sum over all the particles of pz of the ith particle plus the sum of, let's call it p, P will now stand for px and py. Let's use little p. Little p stands for px and py. Little p squared over twice big pz plus m squared over twice big pz. No. No. There was a pz up here and a pz squared down here. Okay? Good. I don't need to put brackets in. Okay, first observation. If we believe in momentum conservation, which we do in this class, if we believe in momentum conservation, then first of all, this is just the total momentum of the system. The first term here is the total z component of momentum going down the z-axis. It's huge, very large, but it's a constant. It's a constant, and as various things go on in this system, the total momentum never changes. If you have a constant term in the energy, which doesn't change in any way during the course of a constant additive thing, adding it to the energy or subtracting it from the energy doesn't do anything. For example, if you added the electric charge to the energy, since electric charge is conserved and the only thing that's ever important in physics is differences of energy, you could just drop it or keep it, it doesn't matter. The same is true here. You have a conserved quantity which is conserved for other reasons than energy conservation. Energy, of course, is also conserved, but Pz is conserved for other reasons. Here's something which never changes. You can just drop it. If you were to think of the energy as being the Hamiltonian of a system, it would make no difference whether you drop it or don't drop it, because it's a conserved quantity which never changes. So you can drop this. It will make no difference. The rest of the energy here is this thing here. Now, first of all, notice that Pz is in the denominator. What does that mean? Why is the energy so small? In particular, energy differences. For example, differences depending on the state of motion in the xy plane, They will be tiny. Why are they tiny? Anybody know? Why are the energy different? Okay, I will tell you. For this, it's useful to remember a bit of quantum mechanics, even though we don't need to be doing quantum mechanics. What is the meaning of the energy? The energy, of course, in quantum mechanics is the same as the Hamiltonian. It is also in classical mechanics. But what's the meaning of the Hamiltonian in quantum mechanics? Do you remember your quantum mechanics? It is an operator. It's a Hermitian operator, but it's also the It's an eigenvalue of the energy, but it's also associated with something else. It's also associated with time evolution. All right? Remember that this is the same as I d by dt, namely I h bar, probably d by dt. This is its action as an operator on a state. That what it means to say energies are very small is that systems are changing very slowly. This is also true, incidentally, in classical mechanics. I just point this out in quantum mechanics. If the energies of a system are very, very small, it means changes take place very, very slowly. The smaller the energy, if the energy scales with some 1 over pz here, it means that the larger that pz is, the slower things take place in the system. What's going on here? Very simple. It's time dilation. The more you boost the system up to higher and higher momentum, in your reference frame, the slower things take place. Okay, that's interesting, but of course, we have all the time in the world. A system moving, we can wait as long as we like to see things take place. If we're trying to make a theory of radioactive decay, sure, boosting it up will make the radioactive decay go slower, but we can rescale that out. We can say instead of working on a scale of microseconds, we'll work on a scale of millions of years, and we'll also see the nucleus decay. Everything just has to be rescaled. So this 1 over pz there, the total, this is the 1 over pz, this is incidentally for the ith particle, and we add them all up. So the fact that all the pz's get large, incidentally, in fixed proportion, they all get large in fixed proportion, that said the energy got small, and that's a completely expected phenomenon. Apart from that, if we rescale all the pz's, ignore the fact that they get big, or just rescale the evolution of the system, this Hamiltonian, or this expression for energy, really does look like the non-relativistic expression with respect to the motion in the xy plane. For the motion in the xy plane, the energy is proportional to the square of the xy momentum, just as it is for the non-relativistic particle. But notice that the role of the mass of the particle in this non-relativistic analogy is not the rest mass. It's the momentum along the z-axis. What this means, what is mass? Mass is inertia, right? It got to do with the difficulty of deflecting something. What this is saying is that the momentum along the z-axis is functioning as a kind of inertia with respect to forces in the perpendicular direction. And the whole thing is looking very, very much like, if we think of pz as a constant, then all this is the non-relativistic formula for the energy of a two-dimensional particle now. Notice we now have only 2 dimensions of motion. And what about this term over here? How should we interpret that? Again, remember that we think of pz as being independent of the state of motion, at least the 2-dimensional motion. So with respect to this 2-dimensional analogy between relativistic and non-relativistic physics, it's an analogy between relativistic physics and 2-dimensional motion, in which pz plays the role of the mass. And how about this object over here? It plays the role of the binding energy. Does it have the right properties to be a binding energy? The only thing about a binding energy is that it should be independent of the state of motion. It should not depend on, this does not depend on the two-dimensional motion. So this is kind of interesting, and it's not only interesting, it's incredibly useful in studying particle dynamics, and absolutely central to studying strings, is that in a very precise and exact way, the motion of a relativistic system, when it's boosted up to enormously large momentum, behaves completely non-relativistically with respect to the motion in the plane perpendicular to the boost. Okay? It's for this reason that string theory is also often described in terms of mathematics, which is the mathematics of a non-relativistic string. A non-relativistic string is a collection of point particles in some limit in which we let the point particles get more and more continuous, or moving non-relativistically. By what chutzpah do we use non-relativistic physics to describe anything as complicated as a relativistic string? Well, the answer is that in the infinite momentum frame, which these days is called the light cone frame, mostly because it has nothing to do with cones, nothing whatever to do with cones. I'll tell you another time why it's called the light cone frame. Not important. But in the infinite momentum frame, motion is non-relativistic, and you have a chance that perhaps the motion of a string, when it's boosted up, may be described by a kind of non-relativistic quantum mechanics. And this seems to be borne out, not seems to be, this has been the techniques that have been used since the very beginning of string theory to analyze relativistic strings. Let me show you the simplest fact. Let me show you one of the very simple connections that follow from thinking this way. Let's now hypothesize or postulate that we can think of particles as strings using the two-dimensional analogy with non-relativistic physics to explore those strings as if they were conventional non-relativistic, not shoelaces, but something closer to rubber bands. Stretchable, they can move, they can flap, they can do all the things that a rubber band, an ideal rubber band, can do. What's the mathematical description of a two-dimensional rubber band which is moving around in 2 dimensions? Okay. Let's take our rubber band to be an open rubber band. That means somebody took a scissor, cut it, and opened it up. Let's begin with open strings. Open strings mean strings with 2 ends. There may or may not be something interesting attached to the ends, but we're interested more in the strings. Let's write the physics of a string. What is the energy? What is the energy stored in a string? All right, we can think of the string as a collection of points. Point particles, which later on we will take limits. One of the things we will do when we take a limit is we'll let the mass of each point go to 0. That's because we're going to have the whole string has a finite mass. We're going to think of it as being a collection of a virtual infinity of point masses. It had better be that in taking the limit, we let the mass of each point go to 0. All right, but what's the energy of this? The energy is going to be proportional to the kinetic energy. It'll be the sum over all the points of xi dot squared. These are 2-dimensional now, so we could write this as x plus y dot squared. That's the ith point, divided by 2. And we might put here a mass of the ith particle, which later on we're going to let go to 0. But let's not be too, I'll just tell you how to do the continuum limit. I'll show you how to do it. I'll just tell you how to do it. All right, what are we missing out of this formula? Interactions. Yeah. These points are attracting each other. If they weren't attracting each other, they would just fly apart. They're forming a string. They are, in addition to the points, we have to put in the little springs that connect them. So think of it as a chain of little balls and little springs. Can you see the springs? All right, little balls and little springs. Let's just call this x sub I squared. X sub I squared now stands for x dot squared plus y dot squared. Okay, what is the potential energy between the points? The potential energy is a sum also over all neighboring pairs. So there's another sum over I here. There's a spring constant. Let's just call it K. All the mass points have the same mass. There's a spring constant there. And what is the potential energy between a pair of points? It'll be proportional to the distance between them, xi minus xi plus 1 squared. Probably a 2 there. This is Hooke's law. This is Hooke's law. The energy stored in a stretched spring is proportional to the distance of stretching squared. That's the Hooke's law formula for the... Now, what happens when you go to the continuum limit? In other words, you let the points get denser and denser and denser, more and more of them. You have to do two things. You have to let the mass of each one go to 0, and you have to also let the spring constant, what it is, you want the spring constant to get big or small? Big. Big. Can you know why? Supposing you take a rubber band, and you take a rubber band, a big long piece of rubber band, and you stretch it. It's easy to stretch. Now take 2 points very close to each other and try to stretch them that same distance. Much harder, okay? So the spring constant gets big and the mass gets small, but in the end what you get, just take it from me, what you get is of course an integral replacing the sum. The integral is over a parameter along the string. You have to introduce a mathematical parameter along the string. We can call that parameter, we'll give it a name, sigma. Sigma goes from one end of the string where we can arbitrarily say it's 0. So sigma is 0 at this end. And at the other end, we can arbitrarily say sigma is equal to pi. I could have taken it to be 1. I could have taken it to be 7. It doesn't matter. It will be useful to call it pi. The reason is later on we're going to study closed strings, which go all the ways around in a loop, and it's nice to say they go from 0 to 2 pi. That's all. But they go from 0 to pi. So this sum over the mass points is going to be an integral from 0 to pi d sigma. This is adding them all up. And we're going to have the kinetic energy of the little element of string at point sigma. We have a continuous string now. We take a little element at point sigma. We take its velocity squared and divide by 2. And what about this term over here? I've chosen the mass to go in the appropriate way. I'm dropping the mass here. By the time you're finished, you can absorb the mass into something else. Doesn't matter what. It's just x dot squared. It's clearly kinetic energy. All right, what about this term here? What's that going to look like? How about xi minus xi plus 1? What should you replace that with? Derivative. Derivative. This is like the derivative of x with respect to sigma squared. So the other term here will be derivative of x with respect to sigma. This is derivative of x with respect to time. This is derivative of x with respect to sigma squared. This is the energy of the string. If I wanted to write the Lagrangian, you all remember what a Lagrangian is. Energy is kinetic energy plus potential energy. Lagrangian is kinetic energy minus. So if I wanted the Lagrangian, it would be this. If I wanted the energy, it would be with a plus sign. Okay, I'll write the energy. We'll write the energy. Hamiltonian plus. Let's focus for a little bit. I'm going to stop in a few minutes and we'll take a rest. But let's focus a little bit on a string which happens to have no overall center of mass motion in the two dimensions in the xy plane. We're coming back now to here. What we're going to do is use a model for a relativistic string, which is simply based on this kind of infinite momentum thinking, but in which there are only two x's, the two x's moving in the direction perpendicular to the motion. So this could be called x and y, but I'll just call it x dot squared. It really consists of x dot squared plus y dot squared. This one consists of dx by d sigma squared plus dx plus dy by d sigma squared. Is that clear? Yeah, okay. Oh, I just absorbed it. I just chose, oh, sorry, there is a 2. 2 is important. I chose k in such a way to make sure that when I got to the final continuum limit, the coefficient was 1. Remember, it's something that has to vary as you vary the spacing, and it can be chosen in such a way as to make this. And this is the conventional energy of a vibrating string. It has two terms, kinetic and potential proportional to the stretching. This is the xt sigma is the stretching of the string. Okay, I want to point out one interesting fact. This Hamiltonian here, or this expression for energy, is the generalization of this expression here for a system of particles which also has a interaction between them. But the whole thing, the whole object, it may be vibrating and doing things, but the whole object is an object. We can call it a particle. Who's to say it's not a particle? Protons and neutrons have spin, they rotate. There's all sorts of internal motions in particles. We know there are internal motions of particles. Internal motions of atoms, internal motions of quarks inside protons and neutrons. The best bet would be there are all sorts of internal motions in every particle. So this stringy vibrations and internal motions and so forth, that perhaps, not perhaps, but would add up to all the internal motion in the particle, all the internal energy in the particle. The internal energy would be the contributions to the energy from the potential stretching and from the relative motion of the different parts. The overall motion, we'll separate that out soon enough, but the overall motion of the string, the center of mass of it, that would just be treated as the position of the particle. But the relative stretching and the relative vibration, that's internal energy. So, when we calculate the internal energy of this particle, what should we relate it to? We should relate it not to the mass, but to the mass squared. In this correspondence, it's not an analogy, it's an exact statement about the properties of relativity. There's a very precise mathematical statement, which I won't make now, but there was an exact sense in which fast-moving systems are completely non-relativistic in the two-dimensional sense. What would the internal energy correspond to? It would correspond not to the mass of the particle, but to the mass squared. So for a string at rest, think of a string which has no motion in the xy plane. All it's doing is vibrating, and it has internal energy. That internal energy has to be identified with the square of the mass of the entire assembly of constituents of the string. If the constituents of the string are adding up to something that we want to call a particle, then that particle has a mass squared, which is the sum of all of the internal energies inside the particle. Now, this is an interesting fact. We get mass squared for the energy of a particle in this framework. There are some C's around which I haven't tried to keep track of. Yeah. There's C's and there's C's and right. Yeah, I haven't tried to keep track of them, but this connection was something I knew that nobody else knew at the time. I had worked on both these things, so this is interesting. This is exciting. Another fact. Another fact is that a string is not so different than a spring. If you look at the spectrum of energies of a string, it's quantized in pretty much the same way. We're going to do the quantization of it carefully, but the basic fact about the quantization of it is that the string is a collection of springs, and springs have quantized energy. And what's the formula for the energy of a quantum mechanical oscillator? An integer multiple of something. Each time you increase the energy of a spring or a string, the internal energy, by 1 unit, it increases the mass squared by 1 unit. Increases the mass squared by 1 unit.
A quick question.
Yeah.
The energy is m squared. The m is, this is where a simple confusion, is m the mass of the string?
Yeah, it's the mass of the whole string.
The whole string.
The whole string.
And the energy, so if you double the size of the mass of the string, it would be 4 times the energy, because the m squared would be, is that correct?
Yeah.
Yeah.
You've stolen my thunder.
Well, I
Right.
confused.
Okay, but now, let's look at this formula a little bit carefully now and see if we can see anything interesting.
Good question.
Yeah.
The right side you have m squared there. That would kind of connote the rest mass of the system, correct?
It is, in fact, the rest mass of the string in a frame of reference where it's not zipping along, but where it was really stationary.
But the equation seems to be not well describing a photon.
That's right, because a photon is massless. Well, that just corresponds to m equals 0 on the right-hand side. And you're going to ask me, how can this thing be 0? Well, we're going to come to that. That is a very significant and interesting point. We're going to come to it. For the moment, it's just the mass of the entire string, including its internal energy, including its stretching energy, all of the energies that you would normally add up to find mc squared, to find the rest mass. That's what this is here. Okay? It's just a...
Before we go further, this is just classical mechanics and relativity applied so far. We haven't invented any other...
We haven't introduced quantum mechanics yet.
Do things like that.
Nope.
Okay.
But if we did introduce quantum mechanics, we would know that this string would have quantized energy levels, and therefore quantized mass squares. Right? In fact, if we increase the angular momentum by 1 quantum, then the quantized energy, the quantum of energy that would be introduced would be a quantum of m squared, not a quantum of m. Right? So. This was an immediate piece of evidence that moreover, this was one of the hints that There's another interesting fact here. Supposing you took a string which was not moving but which you stretched out to a certain length. Okay? How much energy would it have? Well, then all of its energy would be potential energy, not kinetic energy. Let's calculate what it would be. How big is the x d sigma? Well, if you stretched it out uniformly, then the change in x along the length of it would just be the length of the string. L would just be, we're stretching it out to a physical distance L. We stretch it out to a physical distance L over a distance from 0 to pi, right? All right, so the derivative of x with respect to sigma would be something like L divided by pi. I don't care about the pi's right now. They're not what's interesting. The x by d sigma would just be proportional to the length of the string. Okay? If you stretched it out by distance L and divided it by the range of sigma from 0 to pi, that would give you dx by d sigma. And so we can say that dx by d sigma is proportional to the length of the string. And dx by d sigma squared would just be the square of the length of the string, right? This is Hooke's law. This is Hooke's law for a string. If you stretch it out to distance L, the energy stored in it non-relativistically will be L squared. But that's what has to equal the mass squared. Now we know something interesting about the energetics of this string if we were to study it in the rest frame. In the rest frame of the string, the energy of the string is the mass. We got from mass to mass squared by boosting the string. But if we went back now and we said, look, wait a minute, we know E equals mc squared. That's rest mass. What is the rest mass of this string? And the answer is that the rest mass is proportional to, this is a proportionality factor, proportional to its length. In other words, this string has the property that the energy, if you think about it in its rest frame, if you stretch it out to distance L, it will have an energy which will grow with L and be proportional to L. In the rest frame, it doesn't look like a Hooke's law string at all. It looks like a different kind of string whose energy is proportional to its length. Well, that's very interesting because it fits with another picture. It fits with the picture which I described before of lines of flux connecting quarks and antiquarks. Lines of flux would produce, if I slice them through like this, they would produce a patch of electric or magnetic field here. It doesn't matter whether it's electric or magnetic. Lines of flux in a tube like this would produce a magnetic or an electric field in here. Electric fields have energy, and the energy density in them depends on the field. The energy density along this long tube of flux would be uniform. If the number of flux lines passing through this little area is the same as the number passing through this little area, and so forth, the field strength would be uniform along this tube of flux here. This is, in fact, a property of tubes of magnetic flux and superconductors and so forth. In superconductors, you don't have, of course, monopoles in superconductors, but you can have long lines of magnetic flux, and they have the property that the magnetic field is uniform along them, and therefore the energy density is uniform along them. That means that the energy is proportional to their length. This is a common thing in field theory and condensed matter physics and a variety of different contexts where field energy in a field forming a long string is proportional to the length of the string, not the length squared. It's a different kind of string. Another way to think about it is that the string is made up of a lot of little particles, but as you pull on it and separate the distances here, new particles form in between so as to keep the number of particles per unit length fixed. That's another way to think about these long flux lines. that they're uniform along their length, and as you pull them apart, more particles form to fill the gaps. Then, in that situation, it would also be true that the energy per unit length would be fixed, and the energy would be proportional to the length. This is, by now, actually an experimental fact about hadrons, that you can spin them up, you can stretch them, and they have the property that the energy per unit length is fixed. They have it's called the string tension. The string tension is a constant. That would not be the case in an ordinary Hooke's law if you stretch them. But this is the picture in the rest frame. In the rest frame, the energy of the string is proportional to its length. In the infinite momentum frame, where the physics is all non-relativistic, the energy is proportional to the square of the length, like Hooke's law. So these two kinds of strings, Hooke's law and flux tube, are related to each other. In some sense, they're just the same object being described in two different reference frames, one at rest and one...
Amplify that. If you had an ordinary rubber band and it was vibrating with almost relativistic speeds in one...
No, wait. Ordinary rubber bands, if they vibrate with relativistic speed, we haven't got the vaguest idea how to describe them. We don't want to do that. No. We've made an indirect deduction. We made an indirect deduction. First half of the deduction was, in the infinite momentum frame, everything is non-relativistic, at least in two dimensions. We use that to discover the fact that the stretched energy of a string, which is L squared, because it's described non-relativistically like a Hooke's law spring, is L squared. That is to be related to m squared. Indirectly from that, we conclude that if we were in the rest frame, the energy of the string would be proportional to its length. And that's interesting because there's a wide variety of interesting string-like objects that occur in field theory, not made out of atoms, but made out of field configurations, which have exactly the same property. All right, let's come back in a few minutes. I think I've probably exhausted your attention for today, but let me summarize. Experimental properties of hadrons indicated this kind of excitations along a line. Had we been smart at the time, we probably would have realized that this pattern here is the appropriate pattern for strings whose potential energy is proportional to their length. That's something we actually could have deduced directly from here. That, in fact, why am I saying we could have? I did. That the energy grew as the length of such a string. That was the consequence of this relationship here. All right, that was one fact. Next fact. Relativistic physics in a frame in which everything is moving fast is the same as non-relativistic physics except in one less dimension. And so we can try to build a simple theory of relativistic strings by going to such a frame and just using non-relativistic physics, but in one less dimension. Here it is. Here's the non-relativistic string in two-dimensional space. The only thing we have to remember is that wherever we saw energy, we have to think of it, or internal energy in particular, internal energy should be really identified with the square of the mass, not the mass. Okay? That, if you remember, came from the two different expansions. If you like, one of them was an expansion in which this was the big term, and then the whole thing is approximately of order mc squared, square root of this thing in here. The other expansion was a term in which this was big, and then the excess energy was proportional to m squared, not m. So when you do that, and you go through this little exercise, your conclusion is that the Hooke's law energy of the effective non-relativistic string should be identified with a mass squared, which indirectly tells you that, that the rest mass of the string is proportional to its length. And finally, there are lots and lots of field theory and condensed matter systems which have the same property. So that was something encouraging, if you like. Okay, let's take a rest, and then we can come back and either ask some questions or... I don't think I'll discuss the quantization of the string today. The quantization is easy. We've done most of the things that are necessary to figure it out. It's just a collection of harmonic oscillators. But I think we can take a rest first.
Just to help my comprehension here, it seems you start with a classic string, then you boost the hell out of it in the z direction. You basically do a Lorentz transform. Shouldn't you get the same physics when you go back? Shouldn't you get back to the physics that you started with?
You do.
But
You do. It's just easier this way.
No, but you don't have the same physics.
You know?
At first, you started with a string that had a length proportional to its mass square.
In both cases, the mass is proportional to the length, and the mass squared is proportional to the length squared. In both cases. But in one case, you call the energy the mass, in the other case, you call the energy the mass squared. Let's go through that. I'll come back to your question in a minute. Let me just go through it again, because there was some sleight of hand. There was some tricky business there. We wrote that energy is equal to square root of p squared plus m squared, okay? Let's, for the moment, forget the motion in the xy plane. Let's just concentrate on the z direction and the time direction. Energy is related to time, p is related to space. There's two ways I could expand this. One of them is good when p is small and m is large. All right, in other words, when when the particle is moving slowly in my frame of reference. In that case, let's see what we do. Then we write that this is equal to p times the square root of 1 plus m squared over p squared, right? Sorry, I want to start in the situation where p is small and m is large. Good. P is small and m is large, so I write this then as m squared times 1 plus p squared over m squared. P is small and m is large, so p squared over m squared is a small quantity. Okay? Nod. Good, okay. The m can come out, and this becomes m times the square root of 1 plus p squared plus m squared, but that's approximately 1 plus p squared over 2m. Okay? Squared. Which is equal to m, which really means mc squared, plus p squared over 2m. So in that context, the internal energy when the particle is at rest in space is proportional to the mass. That's your good old E equals mc squared. Okay. And that tells you that for a particle at rest, its inertia, a particle at rest, its inertia, in other words, its usual resistance to acceleration, is the same as its mass and its energy. Its mass meaning inertia, and its energy are proportional to each other. Okay. Now, let's do the other expansion. The other expansion, we boost like hell so that the momentum is very large. Okay. And then we expand it in the other way. Let's see, p is very large now. So this is the square root of p squared times 1 plus m squared over p squared. Which is p plus, did I do that right? Yeah, p plus m squared, I think, over 2p. All right. Now this is the momentum along the direction that we did the boost. There are two other directions of momentum, and we could put them in here. But notice that the energy, apart from this fact, this piece, which is just total momentum, which we can drop because it drops out of all interesting things, is proportional to the square of the mass. So in this form, the energy is proportional to the square of the mass. And what that says is that if a particle or a system of particles is moving down the axis with an enormous momentum, that its inertia relative to this direction here, well, let me go back. Let me put in here the other terms, plus px squared plus py squared. They just went together with m squared. This was pz squared plus m squared plus px squared plus py squared. We're taking this to be small and pz to be large. Okay? One of the things that this says is that the inertia is now not the mass of the particle, it's the momentum along the z-axis. And that actually makes a lot of sense. It's not true non-relativistically, but relativistically it is true that a given force perpendicular to the direction of motion will produce a smaller acceleration the larger the momentum. So that's the first thing. This p here is the inertia, and the m squared is playing the role of an internal energy, or m squared over 2p is playing the role of an internal energy. So internal energy becomes mass squared in this frame, and inertia just becomes pz. Oops, that doesn't look good, but... All right, now somebody asked me about the connection between these kind of strings, which have this property of having an energy per unit length, and superconductors. I think I mentioned it as we were talking. I will spell it out. Superconductors have the property of repelling a magnetic field. They repel, they don't want to accept magnetic field penetrating through them. And they actually repel the magnetic field. Because they repel the magnetic field, it's kind of a pressure that was pushing magnetic field out of the way. But if you somehow push a magnetic field, I'm going to tell you how to do that in a minute. If you push a magnetic field into the superconductor in such a way that the lines of force are passing from one side of the here's a big piece of superconductor, lines of force are passing through it like that, what it will do will be to squeeze, will push those lines of force out of the way and push them into a narrow string-like thing, like that. That's called a fluxoid. It's called a fluxoid or a superconducting flux line. Superconducting flux line, magnetic flux, not electric flux, magnetic flux. And how can you make one in principle in a superconductor? Here's what you might do. I doubt very much, well, this is probably not the way it's done in really, but you take a piece of superconductor, you drill an incredibly narrow hole through it. This is a Gedanken experiment. This is not something that I want you to go away with as a practical experiment. You drill through it an incredibly small, let's see, am I going to get this right? Before you cool down the superconductor, you take a long bar magnet and you stick it through the hole, like that. Flux lines come out this way from the bar magnet and this way. Now you cool it down so that it becomes a superconductor, and you draw out the magnet. These lines of flux here will get pulled into the magnet. Even after you've pulled out the magnet, the lines of flux will go through that magnet and they will form a thin tube through that magnet. The field along the tube will be uniform. And because the field is uniform, that means the energy per unit length is fixed. Okay, now let's go a little bit further. Imagine that we had magnetic monopoles. We can actually simulate magnetic monopoles, but let's suppose we really did have magnetic monopoles, that there really were magnetic monopoles in the world. And there may well be, but we haven't discovered them yet. But let's suppose we had discovered them and we could manipulate them. Okay, then we could take a monopole and an anti-monopole, put them right on top of each other, don't let them annihilate, keep them a little bit apart. Take them and put them into the superconductor, monopole and anti-monopole. I'm not going to tell you which one is which, I'm just going to draw two of them. And of course the monopole and the anti-monopole have some flux lines between them. Now cool down the superconductor and take the monopole and the anti-monopole and start to separate them. What happens? Exactly the same thing that we think happens between a pair of quarks, except that this is just an ordinary magnetic field between the monopole and the anti-monopole. So inside a superconductor, a monopole and an anti-monopole would have an energy which would be proportional to the distance between them. Why the distance between them? Because the string between them has an energy proportional to its length. Okay? The monopole and the anti-monopole could not separate from each other. They would be confined because as you start to separate them, the energy goes up with the length, and that's the character of what happens to hadrons, or quarks in a hadron. You separate them and their energy goes up. So okay, so this is a system for the energy is proportional to the length, and it has the characteristics of the same kind of string. Does that answer your question, whoever asked me? I don't know who asked me. Oh well, I guess he's gone.
So the question was, what's taking the role of the superfluid for the hadrons? What is the superconducting fluid?
Virtual monopoles. That's what it's thought to be, virtual monopoles, but not these different monopoles, chromodynamic monopoles. In the superconductor here, the condensate, the superconducting condensate, is made out of electric charge, and it causes confinement of magnetic charge. In quantum chromodynamics, quarks are confined, and they are kind of the electric charges of quantum chromodynamics. The things which condense are magnetic charges. You say, where are those magnetic charges? Why don't we see them? Because they're always condensed in the vacuum. So, but this is beyond what I had intended to talk about today. Okay, what other questions come up? Oh, it's almost 9 o'clock. Okay, yeah.
So the energy being proportional to the length is the rule for highly relativistic string.
Well, a superconductor is not a highly relativist. It's also
not a string.
It's no, but it's string-like.
So if you took a regular Hooke's law string made of springs and had it going relativistically inside,
It would break apart. That's all.
Assuming you could.
You have to make up some theory. I don't know. You have to make up some theory.
But that construction would then have an energy proportional to its length.
I don't know what it would do. Depends on the details. No, there's something special about energy that grows with length. As I said, what it really means in particle language is that as you separate the constituents of the string, as you pull it apart, the energy of pulling it apart, instead of just separating and making larger distances, makes more particles, so that the density of them along the string always stays the same. That's the character of these kind of strings. And the other way to think about it is they're strings made up out of field, where because field lines are not allowed to end, as long as the field doesn't spread out this way, it has to remain uniform in the other direction. So it's a characteristic of flux lines which are confined to a tube. If you're at any kind of situation where an electric field were confined and prevented from spreading out in the perpendicular direction, the energy per unit length of it would be constant. Yeah.
What about the kind of residual motion along the PZ direction?
Along the that's a very good question. Yeah. Remarkably, the way string theory works is there are not independent degrees of freedom for motion along the other direction. This is a remarkable and strange fact that in string theory you do not include directly degrees of freedom for the motion of the string along the direction of the boost here. It is thought that that's connected with something called the holographic principle, that really in a gravitating system you need one less direct dimension to describe it, but it's one of the very remarkable features of string theory that you don't describe the string in, let's say, in three-dimensional space. In this limit, you describe it only by the two-dimensional motion. And yet, as we will see, it's consistent with Lorentz invariance. Yeah.
How many data points do we have on the Reggie plots now? 5 or 10 or?
I don't know what the maximum number is now. I don't know, 7, something like that. It's not endless, but it doesn't give any evidence of giving out. I'll talk about it another time, but the evidence for that. But remember that we're not really interested in hadrons. I was just giving you a historical perspective of where the whole thing came from. But now we want to study this mathematical theory and not insist that it looks like hadrons, but just ask what it does look like. And what we'll find out is that it looks more like gravity than it does hadrons.
What if it was a lepton? What if it was something that is...
What was an electron?
Well, the idea that we had some kind of spatial element of the particle, the compositeness of the particle, for a particle that doesn't seem to be composite.
Well, okay, let's be all right. So the question can be expressed in two different ways. Let's see. It can be expressed, or the answer to your question can be expressed in terms of the smallness of the particle or in terms of the energy that it takes to increase the particle by 1 unit. All right, so let's do you remember the formula for the energy of a rotating system as a function of its angular momentum? L squared, where that's the angular momentum, divided by 2 times something. Remember what it is? Moment of inertia. And what's the moment of inertia related to? The mass and the square of the size of the system, right? mr squared, not m squared, r squared, mr squared. But the point is that for a given mass, the moment of inertia gets smaller and smaller as the system gets, the moment of inertia gets very small when the system is very small. Now, what is L? L is angular momentum, and it comes in quanta. So this is proportional to n squared h bar squared, or something like that. And now you can ask, how much energy does it take to go from n equals 0 to n equals 1? N equals 0, the energy, it might be a little bit of energy, but the energy, this piece of the energy is 0. The first excited state will have an energy h bar squared over 2 times 1 divided by the moment of inertia. And if the object is very, very small, the moment of inertia is very large. No. 1 over the moment of inertia is very large. So the excitation energy, the energy that it takes to increase the angular momentum by 1 unit, becomes very, very big if the object is small. Well, hadrons are big objects. They have small moments of inertia on the scale of quantum gravity. Hadrons are just enormous. I mean, they're big blobs. They have large moments of inertia. The energy taken to excite one is not very big. Electrons are known to be much smaller. The expectation is that they're exceedingly small, maybe 10 to the 16th times smaller than a proton. You square their radius to get the moment of inertia, so that could mean 10 to the 32 times a smaller moment of inertia, and that means that the energy of excitation would be 10 to the 32 times bigger. Well, maybe that's probably too much. But so if electrons have excited states, because they're so small, if they have rotational excitations, those rotational excitations, well, I think I lost my true Fauci plot. But the mass necessary to increase the angular momentum by 1 unit would be way off on that end of the plot. Just too much. It just takes too much energy to spin it up. When I say too much, I mean too much compared to the energies that are available in particle collisions. Okay? So the energy needed to excite a hadron by 1 unit is roughly of order of GeV. You collide particles at a GeV or whatever it is, you see these excitations. The energy needed to spin up an electron is very much higher. You don't see them. How about the energy needed to spin up a basketball by 1 unit of angular momentum? Very small, very small. In fact, you can't even see that it's quantized. Right. So
an atom, it'd be okay.
Whatever it is, first a couple of electron volts. You mean to spin up an atom by 1 unit? Yeah. A couple of electron volts. Good. Okay.
For more, please visit us at stanford.edu.